Hi, my name is Martin Fischer. I'm the Kumagai Professor of Civil and Environmental Engineering at Stanford University. Along with my colleague Ernestine Fu, Adjunct Professor of Civil and Environmental Engineering at Stanford University, we'd like to welcome all you students in Saudi Arabia to our session on robotics, drones, and autonomous vehicles.
Welcome to our session on robotics, drones, and autonomous vehicles. Over the last several years, we've made significant progress in the development of robots, drones, and autonomous vehicles, particularly as it relates to the size, scale, maneuverability, and intelligence of these systems. The term robot means different things to different people, and even roboticists and engineers themselves have different notions about what is or is not a robot. To me, a robot is a machine with a level of autonomy that makes it capable of sensing its environment, carrying out computations to make decisions, and then performing actions in the real world. Typically, robots can do three things: sense, compute, and act. To sense the world, robots can use anything from a simple obstacle detecting sonar to more complex sets of multiple sensors consisting of cameras, gyroscopes, and laser rangefinders. The compute part of robots can then involve anything from a small electronic circuit to a powerful multi-core processor or clusters of networked computers. And finally, for the action part, this is where the robot can perform actions like moving around, manipulating things, completing specific tasks, and whatnot. Overall, these three components of sense, compute, and act vary widely from robot to robot. When defining robots, it's also important to understand the notion of autonomy. Oftentimes, we say that robots are autonomous machines, but the level of autonomy differs for each robot. Some robots can run without any kind of human intervention, while other robots are remotely controlled by human operators. And many other robots rely on both remote control and autonomous behavior. In recent years, technological advancements in software and hardware engineering have enabled the deployment of robots in highly unstructured environments. These advancements have greatly enhanced what humans can accomplish in terms of safety and productivity. Here are some examples of robots. This is Eric. It's one of the first humanoid robots ever developed. It was exhibited at the annual exhibition of the Model Engineers Society in London in 1928. The robot moved its hands and head and delivered a speech at the event. This is another robot. It's designed to play table tennis against a human being. This is Big Dog. It's a military robot that was designed to serve as a robotic pack mule to accompany soldiers across rough terrain. Unfortunately, the project was shelved after Big Dog was deemed too loud for combat. This is the Roomba. It's a robotic vacuum that navigates around clutter in your home, cleans your floors, and then returns to its charging dock when it's finished moving around. This is Curiosity. It's a robot that NASA sent to explore Mars. It's a car-sized rover designed to explore the Gale crater on Mars. This is the Da Vinci system. It's a surgical robot that is designed to facilitate surgery using a minimally invasive approach, and it's controlled by a surgeon from a console. Here's a photo of a drone. A drone can be seen as an aerial robot. It's also known as an unmanned aerial vehicle, or UAV. It flies through the air without any human pilot, crew, or passengers on board. Flying has opened new opportunities to robotically perform tasks such as search and rescue, observation, mapping, inspection, maintenance, and whatnot. Over the last several years, drones have become cheaper to produce at scale, and they have become equipped with advanced sensors and navigational intelligence. All this has resulted in increased interest in aerial robots over the last few years. Finally, here's a photo of an autonomous vehicle. An autonomous vehicle can also be seen as a robot in that it can perform our desired tasks in an unstructured environment without continuous human guidance. Autonomous vehicles have also been referred to as self-driving cars or driverless cars. They are seen as the future of mobility, and there's a lot of hope that they'll be able to be driverless, efficient, and able to avoid crashes. The hope is that they're capable of sensing our environment and moving safely with minimal human input. In this session, we'll discuss the state of robotics, drones, and autonomous vehicles. We'll discuss several key concepts empowering this technology, the range of applications of these technologies, and also some of the important ethical considerations around these systems. In the first part of this session, we have a fireside chat with roboticist and Stanford professor of computer science, Osama Khatib. Osama will share with us how he got into the field of robotics. He'll also share some of the core technology and systems that come together to make a robot work and what's limiting the performance of these systems today. We'll also discuss current and future applications of robots. In the second part of the session, we have a fireside chat with Tom Ryden. He's the executive director of Mass Robotics, which is an innovation hub in Boston that was built for the robotics community. Tom will share with us how he was inspired to become active in the robotics community and how he defines the sector. He'll also share some ways that robotics might be used to benefit society, but also some of the societal and ethical issues surrounding the deployment and development of these technologies. We'll also discuss some common themes and challenges facing robotics technology. With that, I'll turn it over to my colleague before we then dive into hearing from Osama Khatib and Tom Ryden.
Osama Khatib is the Weichai Professor of Engineering and Professor of Computer Science, and by courtesy Electrical Engineering at Stanford University. Osama is a true pioneer and thought leader in robotics. His work focuses on many advanced topics, including autonomous robots, cooperative robots, human-centered robotics, haptic interaction, dynamic simulation, virtual environments, augmented teleoperation, and human-friendly and safe robot design. With these advancements, Osama's research team is exploring applications in healthcare and wellness, industry and service, farms and smart cities, and dangerous and unreachable settings such as deep oceans, mines, and space. Osama is a fellow of the IEEE and holds a doctorate degree in electrical engineering sub aero in Toulouse, France. How did you get into robotics? For example, what was the first robot you remember seeing, and what impressed you about it?
Yeah. So actually, I feel very lucky because I came to robotics from AI. I was working on projects that involved reasoning and development of algorithms to manage transportation. And my project was very successful. At the end, the professor was asking me, wouldn't you be interested in a thesis in robotics? And I said, robotics? Wow. It was completely new, robotics at the time. And I get to really be involved in a very exciting adventure because we didn't have any robot at Supiro where I was working. And I was doing a lot of things in simulation. And then I went to Montpellier, where actually I did my master's, to work with a robot. And this robot is called Manipulation Arm, MA. And the number is 23. I still remember MA23. It's a cable-driven arm that was used in electrical nuclear energy centers where you cannot go inside. So they were using an interface to control it. And I had access to this robot, and I implemented the theory that I developed in simulation. And it was successful. It was amazing when this algorithm worked. I was doing collision avoidance in real time at a time when the computers were really slow and memories were very just unbelievable.
So it's interesting that you got started with developing robots for situations where it's very dangerous for humans. Is that the main area of application for robots, or is that just one of many main applications? So how should our listeners think about the application of robot in sort of major types or categories?
Yeah, this is a very, very good question because, I mean, people have been familiar with robots that were used in industrial manufacturing tasks. And in the early years of robotics, we just promised everything. Yeah, we're going to use all these novel new technologies to solve the manufacturing problem. And it turned out that it's very, very difficult to deal with unstructured environment. So the industry and manufacturing was really working on ways to use robots. But to do that, they had to develop fixtures and jigs and all kind of mechanisms to deal with the whole assembly problem. And that came to be very successful. In fact, the success in manufacturing made it like, I mean, we don't think about it, but every day we have tens of thousands, even millions of robots running all around the world doing a lot of production. These robots are completely pre-programmed. I mean, we spend a lot of time pre-programming these robots by thinking about how we are going to avoid these structures and move, but we spend all that time to program them. And once we finish the programming, these robots are like machine repeating the same task over and over. So the problem is sort of solved for structured environment. But when Martin, you and me, we say, okay, how are we going to use robot to do painting? How are we going to use robot to do bolting? Well, it's completely unstructured. I mean, you can use cameras, but you will never reach the precision and accuracy that was required by these other robots that were bulky and heavy and precise. Now we need robots that come and interact with the environment that we know sort of, but they need to accommodate errors. They need to feel their way, and they need to work like human. So this is basically what we are doing. And what we are dealing with now is a completely different problem that is very challenging. Challenging because we don't know the environment, we need perception, and we don't have a pre-program, we need skills. We need to abstract the capability of the robot. Instead of giving the robot all the details of the trajectory, now the robot has to discover the trajectory from a strategy dealing with the problem that the robot is perceiving partially, and all of that. So it is a completely different problem, and it's very exciting for us because that is where we're doing the research, and we are seeing that actually even with all the things we are doing, we still need the human, and that is where the interface to the human is important. The future of robotics is really in creating this interface, smart interface between the human and the machine, where the human is going to control maybe 10 robots. And at very high level with speech, haptics, or some program, but very high level. And the more we build autonomy, the more we are going to be able to do at higher levels. So this is the thing that we're working on.
Yeah, that helps me a lot. Think about robots. Actually, that clears up some misconceptions I probably had, and maybe many people have about robots. It seems like there's robots that function in a structured environment, and the task is really to set up the environment, to sort of bring the environment and the robots together and program for that environment. And if you took the robot somewhere else, then would have to redo all of that. Then, so the next level is give the robot some autonomy, some perception of the environment, so they can move or react to surprises that could be in that environment. And then I think the exciting part now is that the robots and humans really complement each other, and requires this feedback, this haptic interface where we can almost, it's like we are the robot, and then we teach the robot, so the robot becomes a bit like us. So this is, terribly exciting set of opportunities here. Yeah, I find the application that you are doing with Ocean One or Ocean One Cable Life now really, really exciting. It's one of the most exciting developments for me that I know of. That's why I was excited when we could do this interview. But you've mentioned other exciting applications in surgery, in dangerous work that's societally important. What is the most exciting application that you see today?
So underwater is amazing, but think about underwater. Underwater, you're floating in the water. Now you can go to space, and it is the same problem. You have a vehicle with arms and cameras, and you are now going to rescue satellite, fix them, and bring them or put them back. And there we have a lot of bad machines that are broken, and a lot of debris in space. And they are moving at dangerous speeds and all of that. Now, on the planet itself, we have so many resources that can be helped by. Right now, humans are bringing those, working on bringing those resources. But can you imagine if we start having robots operating offshore platforms, offshore wind farms, repairing the structures underwater and on the platforms? And we have a project right now, exploring a project in that direction of building offshore robotics, so there are no people exposed to danger. And there are a lot of other ideas around those field robotics problems. But if we go to the other applications, so we have art robots. My students every year in experimental robotics, they build projects where the robot is painting or creating a performance, doing sport. We have a project with a student who built two robots playing volleyball and tennis. It's amazing. And they are doing this actually, they were doing this in the virtual world because we were under COVID. And during COVID, we provided them with our most advanced simulation and control systems, and they were able very quickly to build those systems. This is in a class I teach called experimental robotics. So, but the variety of things where we bring assistance to medical applications, not only invasive applications like surgery and others, but all the service. So for the ICU, we developed a concept where through haptics, the doctor will be outside without having to wear all the gears to go in the room, and then interacting with the patient through a very gentle, safe robot to do basic measurement. I mean, just to evaluate a patient, and the number of applications to assist the elderly in domestic environment. And anyway, I think the number of applications around robotics are many, but one important thing to remember is all the applications share the same research problem, scientific development that requires perception, planning, action, interfaces, and understanding of human skills. And this is what is beautiful, because we are working on the fundamentals, and then the applications becomes much more easier.
How would you recommend to someone that's early in their educational journey? How would you recommend they should get started today?
Well, thank you for this question, because sometimes we think, for robotics, I need to study maybe just computer science and develop the algorithm to program this robot. I mean, or for robotics, I need to study how to build a robot. So I go to mechanical engineering. The reality is, robotics is multidisciplinary, and any one who is trying to build a robot or develop a robotic project or make advances with robots is required to understand mechanical engineering, electrical engineering, computer science, and also the connections with biomechanics and all the other specific applications where the robot is going to be used. So this is actually is reflected in every robotics group. You find student coming from mechanical engineering, electrical engineering, computer science. At Stanford, we within each of the different laboratories, we have a mixture of skills coming all together in those teams. So, which means that whether I'm going to be coming from mechanical engineering or going to study computer science, I can do robotics, but the requirement is really to have an open mind and try to not forget, if I'm in computer science, not to forget about physics. And if I'm coming to from mechanical engineering, not to forget about control and about programming. So how can we address this at the maybe the early stages of education? I would say if you want to do robotics, you need to study math, physics, and computer science. And if you have those three basic skills, then you can go further later and specialize and learn how to apply these things together and take the advanced courses needed in the direction you're interested in. So mathematics, physics, and computer science probably are at the base of everything that we are doing in robotics for the perception, for the design, and for the planning and control.
Yeah, no, thank you for this advice to people that are hopefully fascinated about robotics, because I can see that we will need many of them and that need to be working very well. You mentioned many different systems that really have to come together to make a robot work. Can you take us through some of the main ones and what's limiting the performance of those systems today?
So, a robot at the base, you have actuators, and these actuators are connected to a mechanism. These mechanical systems can be a mobile base moving, and you have very nice flat surface you're moving on, and you want the robot to move, and especially for many of the tasks, it would be great to be able to move in any direction. Not like if you have a bicycle or a car, you cannot go sideways. But with a robot, we have that facility. We call it holonomic base. So now just think about how you're going to control this just really simple machine. Well, there are a lot of things you need to see. So you need to have cameras that are going to collect light and extract information and represent it in a map for the human or for the brain of the robot. And then you have controls that are sending commands to the motors that are going to coordinate. And you have different computation done most of the time in a distributed way. So if we take an arm, we have controllers controlling each of the joints separately, and then they are communicating over a network, and then they are communicating to a central computer where you are collecting data from other sensors that have their own. So it turned out like you have multiple devices running on different network communicating, and you are also communicating with interfaces and devices, and all of that makes it that everything should work and should work in real time. And any failure or any incident in one of the components will shut down the whole system. And today, actually, we encounter some of those problems just by some of the mistakes that were done in the software. But eventually, these are very common things that happen. And the only way you can really deploy systems like this is to have a very robust implementation of that network connecting sensory information to be processed, to be communicated to the different controllers, and then be sent to the actuators. And that is another major part in robotics that is becoming more, standardized, because we are seeing a lot of advances in mechatronics, in integration. I mean, I recall in the beginning when we built the first robot that included tactile sensing and some capability of torque control, we have a lot of cables going through the links. So harnessing all these cables is just a major problem, and integrating them in the system. Now we are using Ethernets, Ethercats that handle all the sensory information and allow us to minimize failures in those networks. So eventually, as things stabilize, probably we will have more integration and more robustness in those systems. But still, today we are using different components with different characteristics and trying to connect them all together, and that is not very easy for that aspect of robustness. Robots needs to be robust and safe, and failures has to be done in a way that will not cause the robot to move in a dangerous way to human. So that's a very important characteristic, human or the environment. I mean, a failure on the robot can break as well environment or object in that environment.
I'm convinced that our students, smart students in other places, will solve this problem of bringing the power of the robot with the agility, perception, planning together. And then what comes after that? Are we done with robotic research and we can all enjoy robots? I know that's not the case, but I'm curious, what do you see 5-10 years in the future as the applications and challenges there, assuming the things we are that are challenging today will actually be working?
Yeah, I mean, the truth is there is a very amazing transition robotics is going through right now. And this is the transition from structure to unstructured, from manufacturing to robot in the real world. And this is going to bring a lot of wonderful, amazing, unthinkable applications that will become reality as the technology develop, and in those applications we are going to see more and more abstraction of the interaction between human and those machines, where the machines becomes more and more specialized to perform a task that they are learning from human. And performing those interaction with a human. So the interaction with the human is quite challenging. How can you move around the human? If a robot is just moving like a robot, humans will feel like if a machine is coming from behind you, people will be really afraid of the machine. So how can you be in the context of the human when you're going to interact with the human? How can you be communicating in a way through gestures, through voice, through whatever, those things that are critical in human interaction. And there are a lot of things that we want to do. Like if you are performing a task, a helper needs to be able to interact with you and give you the tools that you need at the time when the tools are needed. And how can a robot understand all these different things? So more and more we are going to see some sort of harmony between the machine and the human in their interaction, and that is something that we're working on today, and we are going to see more and more advanced capabilities built in those systems. But for a long time, I think we will still, except when we have a very specific task, we are going to still see a very big role to the interface between the human and the machine to communicate high-level tasks and to do corrections and to place those constraints that where the robot is going to interact with. And this is going to be very exciting, because now you have almost a real human level helper working with to assist a worker or an elderly or a medical person.
Thank you, Osama, for taking us through brief history, but a lot of the present in terms of challenges and applications, and then a very exciting future of robotics and how it will help us be safer and more productive on Earth and, well, underwater and in space. So thank you, Osama. Tom Ryden is the Executive Director of Mass Robotics. Mass Robotics is a non-profit organization serving as the innovation hub for robotics and connected devices. Prior to his leadership role at Mass Robotics, Tom held many technology-related roles. For example, he was the Director of Sales and Marketing for iRobot, makers of the Roomba, one of the most successful consumer robots in the market. He holds a Bachelor of Science in Electrical and Electronics Engineering from the University of Vermont and an MBA with a focus on finance from Bentley College.
For the second part of this session, we have an industry guest speaker who has guided and supported several successful robotics and automation companies. I'm thrilled to welcome and interview Tom Ryden. Tom, thank you for joining us today.
Well, thank you for having me.
Tom, so you've been active in the robotics community over the last several years, and now you oversee a very large innovation hub and office space for robotics companies in Boston. What inspired you to become active in the robotics community?
So I've actually been involved in robotics for quite some time. I graduated with an engineering degree, kind of got involved in actually auto samplers and things like that. And then had an opportunity to join a small firm called Real World Interface that made robots for education. For Stanford had a few. There's little red experimental robots that professors could design other platforms on. I just got hooked. It was so much fun to work with this young company. They ended up getting acquired by iRobot. I then spent some time at iRobot, which was a fun ride as well. And then I've gone on to do some other robotic startups. And now I'm with Mass Robotics, which, as you mentioned, is the home to about 65 robotic startups. We run a shared workspace and innovation center for companies that are doing this type of work.
Thanks for sharing that. So I'd like to start by understanding how you define robotics. And to me, a robot can be anything from, say, like a robotic vacuum cleaner to a robotic arm and assembly line to a remote-controlled military vehicle. And as robotics technologies just keep on growing and maturing, the definition does seem to be quite broad and only getting broader. How do you define the sector? For instance, do we include autonomous driving technology, or what sorts of technologies do we consider under robotics?
Yeah, that's a great question. In our space, we have companies have to apply to get in, and one of the things we do is we look at the technology to make sure it's a fit for what we can support. And the way we define robotics is really there's kind of three main components. We look for a system that has some level of onboard intelligence and the ability to sense and react. So some ability to sense the environment around it and then respond to what it sees in that sensing. And those are two important things. But the other thing that's real key is some level of actuation or mobility. And that doesn't necessarily mean a mobile platform, an autonomous mobile robot. It can be an industrial arm, but something that has motors, actuators, and as I said, sensors and intelligence. That's kind of a broad thing. What you find is that covers a lot of different types of companies and products.
Mm-hmm. And Tom, with that definition in mind, what are some ways that robotics technology might be used to benefit society? For example, in the field of medicine, I'm excited that robotics can create a level of precision that's difficult to replicate with human surgeons, just as one example.
Yeah, I think the way that robotics can impact society as a whole is amazing. There are so many different ways that we are seeing robots used in unique applications that can be extremely beneficial. You know, the first thing you think about, of course, is the dull, dirty, dangerous jobs. We're having a lot of companies that are developing tools to do inspections in everything from oil tanks to caves to obviously looking for roadside bombs and things like that. It's a great use of the technology. But beyond that, as you mentioned, surgery, robotic surgery, assisted surgery, and other technologies to aid in healthcare, exoskeletons, and helping in rehab. And then a big field that's small but growing that we're really excited about is an area of using robots to help the environment. Specifically, there's a company that developed a small robot that traps an invasive fish called the lionfish off of reefs. And so using the robot to capture those fish is a great way. There's just multiplying too quickly for humans to do it. And using that technology is a great example. There are many challenges still with robotics in a lot of these areas, but we're seeing growth pretty much across the board in robotics.
Mm-hmm. It seems that every day there's so many verticals that continue to be transformed by innovation in robotics. You've mentioned a number of them, and anything ranging from warehouse automation, fulfillment, construction, retail, food, agriculture, medical surgery, consumer electronics, and so much more. If I'm a founder looking at any one of these verticals, are there particular verticals that you think have high potential for innovation and startups? And conversely, are there verticals that you think pose particular challenges, maybe either from a technology or market standpoint?
Yeah, so I think first on the opportunities, there's no question that warehouse automation is the most rapidly growing sector of robotics today, and I believe it's going to continue that way. You know, the society has transformed how we purchase goods. We don't buy them in a store. We don't go pick the items. We expect them to be picked for us and shipped to us, and somebody has to do that. And there's not enough workers to physically pick everything that we're ordering, and so that's where robots come into play. And while robots are doing some of those jobs in warehouses today, primarily moving the goods autonomously, there's still big areas that need development, specifically picking, packaging. Those areas can really use help. And I think there's great opportunities for companies to come up with creative solutions in that area. So that's number one. I think industrial automation, where we talk about factory automation and not fixed robots. Obviously, they've been used in automobile plants for years, but this new form of collaborative robots that are really human safe and can work side by side workers. I think there's a lot of opportunities for different applications, smaller, shorter run, more flexible production lines can use this technology. Still a lot of work has to be done around the AI, the vision, the gripping, but those are two interesting areas. Mm-hmm. I think in terms of areas that I'd be a little bit more cautious of is ones that are impacted by regulation. Healthcare being an example. It's tough for startups and many opportunities to kind of pursue in healthcare because they have to get FDA clearance or other clearances. And the same goes for certain things. We know that the challenges of self-driving vehicles. That in particular is, most of the rules of the road are guided by states. And so now if you want to have a different type of vehicle operating even on the road or the sidewalk, you're now having to deal with 50 different states and their rules. And same with drone. At least drones, you have the FAA a little bit better in terms of coverage, but still there's a lot of independent rules, local rules that drone operators have to abide by. So those are areas that, while I think there's a ton of opportunity, they still have some hurdles. And anytime you deal with regulations, you're kind of at the whim of when those will change. And so it's tougher for you to implement the business plan you want.
Mm-hmm, mm-hmm. I'd like to dive a little bit more into common themes and challenges facing robotics technology. You alluded to AI and vision, and I ask because for me, I'm constantly thinking about the use and challenge of computer vision and object recognition in robotics. For instance, in autonomous navigation, we need to think about how we deal with, say, for instance, obstacles, birds, road signs, other spontaneous situational events without the system failing. We also need to think about how we anticipate the unexpected in terms of failures. And we also need to consider how these systems are both robust and resilient to the long tail of possible failure modes. And also when developing robotics technology, weight and efficiency also comes to mind for me. And what I mean by that is it's impractical to have a giant drone that's too heavy to fly, for instance, and we need to consider what equipment can fit under the size, weight, cost constraints of a system. So, Tom, all that being said, what do you view as some common themes and challenges facing robotics technology?
Yeah, so I think number one, and you alluded to this, is power, right? Is battery life and power consumption. There is this desire, as you mentioned, to have bigger drones that carry larger packages and yet have longer durations or endurance. And they just don't go hand in hand. As you add weight, you need to add more batteries or more of another power source, and that adds more weight. And so you're constantly battling this. And that's true across platforms, whether it's a drone, whether it's a ground-based platform. I think a perfect area of example of that is in exoskeletons. There's some great work that's being done in that area, but when a worker wants to use an exoskeleton to help them lift boxes on a line, they want that to work for their shift. They don't want to work for 15 minutes and then have to swap out a battery or have to sit or to it next to a charge dock or whatever. And so we really, I think that is an area that continues to hold back robotics in some sense. The other area that you mentioned, and I strongly agree with, is sensors. There are currently not enough fully robust sensors. And what I mean by that is sensors that cover everything that a human can do. You mentioned self-driving cars. That's a great example. If a car comes up to a puddle today, there's not a good way for the technology to understand how deep that puddle is, right? There's not really something that'll penetrate into the water and say, oh yeah, that's something that you can drive through, or that's a couple of feet deep. You should avoid that. Now, humans have a way of kind of understanding enough around them to kind of guess. And even still, they get stuck. In the recent rainstorm we had a couple of cars, get stuck under a bridge where the water, they thought it wasn't too deep, and the water turned out to be about 4 feet deep and got the car. So, but when it's autonomous, you even rely more on those sensors. And so the ability to have robust sensors that work in all weathers, that work in snow and rain and so forth, that don't get occluded by different elements. And that have that kind of duration and last for the life of the product. I think there's a lot of work that needs to be done on the sensing side.
Mm-hmm. So, Tom, let's take a step back and look into the future. What do you envision our future society looking like with widespread adoption of robotics? How will our day-to-day lives be affected?
I think the area that I'm excited about is certainly elder care and the ability for robots to help in your day-to-day life as you maybe cannot do all the tasks you once used to. And so I truly do see that there will be robots operating in the vicinity around you and helping you in your daily life. And that can be anything from getting you a cup of coffee to helping you in and out of bed, that type of thing. There needs to be an amazing amount of work to do. And also there has to be a lot of thought into the HRI, the human robot interaction or interface, because right now that's an area that I think is kind of falling behind. A lot of folks are focused on the technology and not necessarily how humans will interact with the technology. And as it does become more involved in the home and helping you, you want to be able to just work with that robot in the way you feel comfortable. I think a lot of work that we've seen in Alexa and other technologies like that are going to be implemented on robots so that you can have more of a casual conversation and the robot understands that, oh, maybe you want to get this item or that item or be helped with this. And you don't have to guide it. You don't have to kind of joystick the arm to pick up the cup of coffee. You can just kind of imply that you would like that. Can you take that over to the microwave and warm it up for me? And the robot will understand what you mean by that. I think that's an area that's coming, and that's an area that I think excites me.
Mm-hmm. And finally, an important final question that I think is critical to talk about is the societal and ethical issues surrounding these technologies. How should we be thinking about this? So for instance, who is at fault when an autonomous system causes a crash? Or what about when a robotic surgery encounters complications? For instance, should we allow drones to navigate through indoor environments when they do not have 100% safety guarantees? Tom, how do you think we should consider the societal and ethical issues surrounding the deployment and development of these technologies?
Yeah, we're going to have to weigh the benefits of what the robot is going to do in that particular case versus the risks of it being able to perform that task appropriately. There's a lot of challenges around ethics in robotics. We see that, recently there was one of the dog type robots that had a weapon mounted on it, and there was a lot of uproar about that. Where is that leading towards? We need to have open discussions about that, and also there needs to be work in ethical AI and understanding of the decision-making process and how robots will respond. It's a hard thing to do. I know the Air Force has looked at one of these projects of testing the AI around a robotic platform that learns as it maps. And so if you don't know what it has mapped, how do you know how to test that? And it's an interesting challenge. I think that's going to be an area that we have to continue to focus on. And make sure that these robots are doing the tasks that they're appropriate for and that are in the best interest of us as humans.
Mm-hmm. Lots of things to consider. Tom, thank you so much for joining us today and for sharing your thoughts and insights.
No problem. Thanks for having me.
To conclude today's session, think about how robots, drones, and autonomous vehicles will impact various sectors in our everyday lives. As Osama mentioned in his fireside chat, robots can be used for oceanic discovery, where a robot can go where humans cannot and still embody human intelligence and intentions through immersive interfaces. Robots can also be used in military applications like for reconnaissance and surveillance, or for sniper detection and neutralizing explosive devices. They can also be used in healthcare. For instance, surgical robots can perform tasks with excellent precision during surgical procedures, while the human surgeon takes a secondary supervising role. There's also exoskeleton robots that can help paralyzed patients walk again and be independent of caretakers. Robots can, of course, also be used in transportation, delivery, and logistics in both urban and rural settings. With autonomous vehicles, once the vast majority of vehicles are connected devices, the city and cars can jointly automate things like traffic management, route planning, and demand management for ride sharing. And with aerial robots, drones can be used for product deliveries, agriculture, policing and surveillance, infrastructure inspections, and much more. Teams of drones can operate collaboratively to achieve tasks that aren't feasible with one drone. With all these different applications of robotics, think about the societal and ethical issues that surround the deployment and development of these technologies. There's a famous thought experiment that was devised by the philosopher Judith Jarvis Thomson in 1976. It's called the trolley car problem, and the problem is highly relevant today when discussing the ethics of autonomous vehicle engineering and design, which may require programming situations where fatal conditions are unavoidable. Imagine that there's a runaway trolley speeding down a track. Ahead of it, there are 3 people tied up on the tracks. There's no way they can escape before the trolley hits and unfortunately kills them. Imagine that you are standing next to a lever which allows you to switch the trolley onto another set of tracks, avoiding the 3 people. Unfortunately, there is one person on the new track who is tied up too, and this person will be killed if you pull the lever. Would you pull the lever or not? It's an interesting and difficult thought experiment that we need to consider in the design of autonomous vehicles. Overall, as we continue to make progress for these technologies and systems, we'll be able to reduce manufacturing costs, make longer-lasting batteries, improve computer vision and pattern recognition algorithms, and much more. These systems will be deployed across multiple sectors in our daily lives. At the same time, it's just as important to think about the societal and ethical issues that may inhibit the adoption of these technologies.